Hello friends, in the previous lecture we had started with continuum mass approach. Similar to this, we'll start today with Rayleigh mass approach. Again, it is different from lumped parameter model and more towards the continuous mass parameter. Rayleigh method, it gives faster and accurate computation of fundamental frequency for a continuous system. And as you know, a continuous system is approximated by an equivalent SDOF system. Now, for a given propped cantilever beam here, if I want to find out the kinetic energy stored at distance x when the displacement is y, I'll get it as k equal to half m equivalent v square when it is equivalent SDOF, where v is nothing but change of displacement with respect to time, which will be given as g dot t. Hence, the value of k becomes half m equivalent g dot t the whole square. Now, k for a continuous system can be written as half m bar dx v square, where m bar will be mass per unit length. So, substituting value of v as dy by dt, and here displacement y is in terms of h of x into g of t, that is space and time both. Substituting these values and partially differentiating, the value of k becomes half m bar dx h of x square dot g dot t of t the whole square. So if we compare these two values of kinetic energy and integrating it from 0 to L, I'll get what is my equivalent mass MEQ. So it comes out to be integration from 0 to L m bar dx h of x square. Now if in case you have additional point load at distance a, your m equivalent changes to this particular equation. Now here h of x can be said as displacement at x upon displacement at b. B is the location where deflection is to be found out. Further, if you want to find out strain energy stored in beam and that in spring, for beam it is half m square upon EID square. And it is known that moment m can be written as EID square y by dx square. Substituting that value, we'll have the equation of strain energy stored in beam as half EI h double dot x the whole square into g of t square dx. Here, because differentiation is with respect to x, you'll only differentiate h and not g of t. Similarly, strain energy stored in spring is given as half k equivalent g of t the whole square. Comparing these two, we are able to get k equivalent just as we did for mass equivalent. And in case of point load, this is the equation. The natural frequency is the square root of k equivalent upon m equivalent. In both of these we have just obtained. Further, to solve a numerical, this is what is required. This is from basic structure analysis that load intensity is given as EI and into the fourth order of dy and dx. Similarly, shear force is given as EI d cube y by dx cube. Further integrating it, we will get moment as EI d square y by dx square. Similarly, rotation is further integration of moment as EI dy by dx and deflection as EI into y. Let us take up a numerical. Consider a propped cantilever beam here and find its natural frequency and natural time period. The beam is having a span of 5 meter with cross section of 0.3 width and 0.6 meter of depth. Young's modulus is given as 25,000 megapascal. The approach to be used is Rayleigh's approach. These are the equations from basic structure analysis. For the propped cantilever beam, if you substitute the boundary conditions, and the beam is having length of 5 meters at x equal to 0, the support is a fixed support. So we'll say condition 1 as the displacement y is equal to 0, and condition 2 is that the rotation as well is 0 at x equal to 0. Similarly, condition 3 and 4 are for length x equal to L. So at x equal to 5 meter length, y is 0 as well as moment is 0 at the propped end. So from the first condition, C4 comes out to be 0. From the second condition, C3 also comes out to be 0, constants. From third equation and fourth equation, these are the forms you obtain. In solving equation 3 and 4, you'll get other two constant as C1 as minus 5 by 8 WL and C2 as WL square by 8. So you have got all the four constants C1, C2, C3 and C4. These constants are from these equations. So what you obtain y is 1 by EI into substituting all these values of C1, C2, C3 and C4. Similarly, if you take a reference point at x equal to L by 2, half length of the beam, you will get the equation of y as well. So normalized h of x becomes y of x upon y of L by 2. So substituting these values, you will get h of x as 2x by L whole raised to 4 minus 5x by L cube plus 6x by L square. So as we have obtained h of x, it is easy now to calculate m equivalent and k equivalent. Starting with m equivalent, the equation is known integration from 0 to L m bar h of x the whole square dx. M bar will substitute at the end, so h of x, what we have just obtained in the previous slide, will square that. Here we must know that a plus b plus c the whole square has this formation. So solving this, m equivalent comes out to be 2.14 m bar into L. Similarly, k equivalent has equation integration from 0 to L ei h of x the whole square dx. Again, solving everything and keeping ei and L as variables, k equivalent comes out to be 367.2 ei upon L cube. It is known that natural frequency is square root of k equivalent upon m equivalent, which comes out to be 13.09 square root of ei upon m bar L raised to 4. So for any given beam, for any given propped cantilever beam, if you substitute ei, m bar and L, you'll be able to get omega n. Here, the values of ei, m bar and L can be calculated like this. M bar is nothing but the cross section into density, which comes out to be 4.5 kN per meter, which is equal to 450 kg per meter. E and I can be obtained. E is given already. I is nothing but BD cubed by 12 for rectangular cross section. It comes out to be 5.4 into 10 raised to minus 3 meter raised to 4. So when K is in Newton per meter, your mass has to be in kilogram for omega n to come out as radian per second. Substituting these values, omega n comes out to be 286.8 radian per second, and time period comes out to be 0.022 seconds. And these are the outputs required. Happy learning. Thank you.